Good morning. We have moved on to our third lecture in this course. In the first lecture, we looked at static indeterminacy and how to obtain the static indeterminacy of a structure. In the second lecture, we looked at how to get the kinematic indeterminacy of the structure, and then we quickly looked at various types of structures and looked at what their static indeterminacy and kinematic indeterminacy were. Okay. So, this lecture I am going to be looking at the method of virtual work. This sequence of 3 lectures that we have are essentially to review things which you have already done. It is just that to put them into the perspective of what we are going to be talking about later. The method of virtual work, it is something that you people have known for a long time. You may have known it as a unit force method to get displacements, or you may have known it as a displacement approach to finding out forces. Let us just review what the method of virtual work, it is actually not a method, it is actually a principle. What does the principle of virtual work say? What it says is that if you have a body which is in equilibrium under a system of forces. Now, if you displace the body, okay, then in other words, you give a virtual displacement to the body, then the work done by all the forces acting on the structure is equal to 0. So, what are the important tenets? That the body has to be in equilibrium under a set of forces, okay, and then if you apply a virtual displacement, then the work done by all the forces is actually equal to 0. This is the principle of virtual work. However, understand one thing, as soon as it says it is no longer the principle of virtual work, because the principle of virtual work has 2 methods. If you look at it, there is the virtual displacement method, which is the common one that we always refer to, that you have a system of forces and you subject it to a set of virtual displacements, and then the total work done is equal to 0. Okay. However, you have another method. This is called the virtual force method, where if you look at the body under a set of forces and it has a displaced shape. Okay. If I apply a set of virtual forces on this structure in equilibrium, okay, then the work done by these virtual forces undergoing the real displacements of the structure is also going to be equal to 0. This is known as the virtual force method. Now, what are these methods? Why do we use these methods? It is very important to understand that its principle of virtual work, method of virtual displacement, method of virtual force, big deal. I mean, why do we need to study these methods? It is very interesting. Let's study. The whole principle of virtual work is actually a very interesting principle which changes a geometry problem into an equilibrium problem and an equilibrium problem into a geometry problem. In other words, the principle of virtual work actually provides a kind of taking a real structure into a virtual zone in which geometry is reflected by equilibrium, and equilibrium in the real structure is represented by geometry in the virtual structure. You will see how. If you look at this, what do we use the principal method of virtual force for? What do we use it for? You see, what we use it for is to actually find out displacements. This is what we are trying to find out. So, in other words, finding out displacements mean we are trying to define geometry, the displaced geometry of the structure. But what do? We use the virtual force method. What does the virtual force method do? It actually is you apply a set of virtual forces, find out all the forces in the structure due to the action of virtual forces, and then multiply the real displacements and deformation in the structure, and the total work done is 0. What this gives is it gives me the displacements by actually solving an equilibrium problem. So I use equilibrium to define geometry, and in the next method we want to actually find out the forces by applying displacements. So what do? Well, we actually apply a virtual displacement pattern, find out the displacements and deformation in all the members, and then find out the work done by all the real forces undergoing these virtual displacements and deformations and equate it to 0. So in other words, what do? With this we find out forces in the structure. So we define forces in the structure. And what do we use? We actually use geometry. Because given a virtual displacement, to find out the displacements and deformations of all the joints and members, you require to solve geometry. So you see, it's just the flip side. To define geometry, we use equilibrium. To define forces, we use geometry. And that is, in a sense, the method of virtual work. Now, it's all very fine to say this. Let's actually use this methods, and that will become much more understandable when I actually give you this. So let's use the virtual force method to find out the displacements in a structure. Let's do that. Let me go back to my base truss that I have, and now let me say that I subject it to force F1 and F2, and I want to find out, my question over here is to you, is find out the displacement, horizontal displacement of this joint. That is my question to you. These are the real forces acting on the structure, and I want to find out what is the horizontal displacement of this point under these forces. Okay. Now, how would I do that? Well, actually, let's go through the steps, and that will actually illustrate the concept of how the method of virtual force is used to define the geometry. Simple problem. I'm not going to make it very complicated. I'm not even trying to analyze the structure. Given these loads, find out the displacement. That's my question. How do I do that? Using the method of virtual force. Let's see. The first step is what? The first step is, note that this is a statically determinate structure. I've made it purposely that. So the first step is to find out all the forces in all the members and supports. So I can easily get it. Let me give some numbers. Let me put this. That this is, let's say, 5 meters. Okay. This is equal to 5 and 5. Okay. So this is 5 meters, this is 5 meters, and all of them have the same E and A. All of them are identical. Okay. So I need to find out this. First step, forget this. Take the real structure. Under these set of forces, I find out the reactions. Let me call this A, B, C. So I'll find out R AY, R AX, and R CY. Note that these are all the support reactions that you develop in this structure. Now, can I find these out? I can find these out. I don't want to go into it. You have three unknowns, three equations. One is for horizontal, one is for vertical, and one is taking moments about any point. You can find out RAX, RAY, and RCY. So you know these now. Once you know these, can you find out the forces in these members? Well, I can analyze the truss, right? And I can find out the forces in these members. You use any method, method of joints, method of sections, I don't care how you do it, but given the fact that this is a statically determinate structure, I should be able to find out the force in member AB, the force in member AC, and the force in member BC. These also I can find out. Under, what are these? These are for these applied loads. Okay. I can find these out. Now, once you know these, what else do you know? These are the actual forces in these members. Okay. Now, I can find out the axial deformation in member AB, in member BC, in member AC, and then in member BC. How can I find these out? I can find these through, I'm not even going into, this is something that you should know. The axial deformation is given in terms of the axial force. Right? You know this, that the axial force divided by E gives you what? Axial force divided by A gives you what? Axial force by A gives you stress. Stress by E gives you strain. Constant strain, strain into L is equal to the deformation. So these are things that you have picked up long time ago, and I'm just writing them down. Of course, EA of AB, EA of AC, and similarly for this FBC, LBC upon EA of BC. So in other words, since I know I'm given the EAs, I'm given the lengths, I can find out the lengths, and I can find out the forces, I can evaluate these three. So therefore, these are the steps for the real structure. You find these out. Right? Now the question is, these are the real support reactions, these are the real forces, and these are the real deformations in each of the members. Okay? These I can compute. Given this and given the geometry, undisplaced geometry of the structure, I can always find out all of these. So I have given them. Now let's move on. Now what's the next step? So I found out all the real forces, real reactions, and real deformations in the body. So I know R, I know axial, and I know real. These are all of them, and these are due to the loads F1 and F2 applied on the truss. Okay. Now, what's the next step? Now I'm going to apply the method of virtual force to get my R1 displacement. So what do? The method of virtual force says I need to apply a set of virtual forces on the body. Okay. Now I can choose what I want, and the way I choose is I apply only this. I do not apply any forces here. There's a reason behind it. We'll see. I apply a virtual force. This is a virtual force. Okay. And the point here is that since I do not remember I forgot one thing, and that is that how many degrees of freedom does this structure have? The structure, if you remember, has 3 degrees of freedom. I've already looked at it. Okay, and if I look at the structure has 3 degrees of freedom, what are they? This displacement, this horizontal, and this vertical displacement. So what I'm going to be doing here is I only need to find out this displacement, and therefore if you look at the work done by all the external displacements, what is the work done by the external displacements? They are R1, the displacement that I am interested in, into df plus, you see I have R2 and R3 over here, but they don't have any forces attached with them. So R2 is equal 0 plus R3 multiplied by 0 gives me essentially R1 into delta F. Okay. So my work done by the external displacements is actually just R1 df. That's the reason why I only apply a force here. Okay. So that is the work done by this force undergoing this displacement, the virtual force undergoing the real displacement. Now, what's the next? What are the other things? Well, the other things are that the internal virtual forces will also do work because you have real deformations in the body under the action of forces. Okay. So what I need to find out is under this force, I need to find out what are the forces in the body. So again, I find out Ray, Rax, Rcy. I find those out, and I find out the virtual forces developed in all the members. Okay. In this particular case, it's very simple. Actually, you can say that this is equal to delta F, this is equal to 0, this is equal to 0. You can compute it, and you will see that this is equal to 0, this is equal to 0, and this is equal to delta F. Anyway, I've analyzed it. It's very simple, so I can analyze it. It doesn't matter. I mean, it's not relevant in this particular case. However, I've done it. You can get it. Okay. So now, the one aspect of it is, if you remember, the equation said virtual work, total virtual work is equal to 0. We can also write this in another way. We can write it as the work done by the external displacements is equal to the work done by the internal displacements. Internal displacements, what are these? Well, how can we write it this way? Because actually, if you see, all the internal forces in the structure are essentially reactions to the loads. Okay? So they actually oppose the loads. So the work done by the external displacements and forces are actually opposite. The work done by the internal forces are opposite. So if you look at this equation, I can actually write it in this fashion. If I separate out the internal and external, this becomes this. Why is this minus? Because if you really look at it, all internal forces are reactions. So they oppose the loads. So that's why there's always a negative sign. Okay? And when I take this, this goes into this. Okay? So this is also another way of writing the virtual work equation. So what is the external virtual work in this particular case? You will see that this is the external virtual work. Okay. And what is the internal virtual work? The internal virtual work is the work done by each deformation multiplied by subjected to the forces. So if you look at it in this particular case, the internal virtual work is going to be equal to what is the virtual force in each member? This in member AC, this is A, B, C. In member AC, it's delta F. And what is the real deformation? Delta AC. So delta AC, which we have computed earlier, multiplied by delta F, that's the work done. Note that this delta, by definition, you see this is tensile, so this is elongation. Elongation multiplied by tensile is always given in this fashion. Plus the work done by BC multiplied by the virtual force in it. What's that? 0. Plus delta AB multiplied by the virtual force, which happens to be 0. So what's the internal virtual work? Internal virtual work is delta AC into delta F. Okay? That is the internal virtual work. What's the external virtual work? This. If I equate the two, what do I get? You will see that R1 is equal to delta AC. This is what you get. Now this is not surprising. Let's go back here. This point is not moving anywhere. Now, how much does this move by? Well, it moves by whatever is the actual deformation in member AC. So that's what you've got. You see, the method of virtual work has given me a geometry by actually solving two equilibrium problems. The first one was the real equilibrium problem where you are subjected to the real loads, and the second one is the real structure subjected to the virtual force, virtual load. Okay. This in a sense is how to use the virtual force method to get geometry of a structure. I'm just illustrating these points. I'm not going to be solving anything right now. I am just looking at it purely from the point of view of the principle. Once you understand the principle, we can then use it very easily. We'll be using it for the rest of the semester and all the lectures that I give you. You will be using these methods. So we will continuously be using these methods so that you'll be totally, absolutely certain of what to do when you come to it. Now let's look at the method of virtual displacement. Virtual displacement. What is the virtual method of virtual displacement? Let me look at this. Same structure. You see, the whole point here is I'm going to get you so involved in this structure that same truss structure. Now I have a set of forces. Again, the same set of forces. I'm going to use method of virtual displacement. What is method of virtual displacement used for? Used to solve equilibrium problems. Okay. Now what does that mean? Let me say in this particular case. Due to this set of forces, I need to find out what this is. RCY. I want to find out what this reaction is. Okay. Now, since it is a statically determinate structure, you can find it easily using equilibrium. But I want to illustrate the method of virtual displacement to you. So we are going to assume that you don't know how to solve equilibrium problems. Let's assume that. And can I get, without solving the equilibrium problems, can I get this reaction given these set of loads? That is the question here. And I have to use the method of virtual displacement. How do I do that? Well, let's see. what I do is, here I say that, well, under these set of forces, the structure is in equilibrium. Okay. So what I'm going to do is, I'm going to apply a virtual displacement. And note that I want to find out this reaction. So what I do is, corresponding to the reaction that I want to find out, I release the restraint. Release the restraint. Okay? And I give a unit, or maybe not unit, forget it. Just give it some displacement. Delta, delta. Okay? In other words, what I am doing is, let's be very clear about it. All I am interested in is to ensure that this structure, now note, if you look at this, once I remove this restraint, this is a mechanism. Since it's a mechanism, it's a single degree of freedom mechanism, I can give it a displacement and I can find out how every other point moves. Is that clear? I can do that. So now what? Now here, and note also another thing, that this displacement, since it's a mechanism, is not going to lead to any deformation in any of these members. In other words, I can move this body as a rigid body because it's a 1 degree of freedom redundant. 1 degree of freedom mechanism. Okay? So, I give it a displacement. And what do I do? Well, given this displacement, I need to find out the displacements of all other points. So, this is a geometry problem. Let's see how I can do that. Let's look at this, and let me again go back to the particular problem that we were looking at, which is, I know the geometry. I need to know the geometry to be able to give you the geometry. Okay. So I give this a displacement d delta. Now, will this move in this direction? See, note that this joint is here. Okay, this point cannot go anywhere. And I need to move this way. It does not mean that it only moves in this direction. You have to ensure that every point moves the way it does in a rigid body. In other words, you cannot have deformations in any of the members. Remember that the displacement that I give, although I'm showing it to be very large, is actually very small. Okay, so small displacements still hold true. The virtual displacement that I give has to be a small displacement. Okay, I might show it as very large, but I'm just essentially exploding it to show you. Okay, it's not as if it's going to be moving in that direction. So note that for this member not to actually deform, it is free to move in this direction, tangentially. Okay, if it moves anything in direct direction, you're going to have axial deformation. So you cannot. So that means this point can only move up here. Okay, so therefore, look, I'm going to show this. It may look it longer, but remember that this length and this displacement is very small compared to this length. So although it looks longer, it really isn't. Okay, it's just that I've exploded the view. So this one goes this way. Now I need to know where this point goes. Okay, so how do I do that? That's the geometry problem. Okay, what I need to do is understand that this joint, this member, it's connected over here, and since it cannot deform axially, the only way that it can move is along this direction. Okay, it can move along this direction. Now how do I get where it's gone? Has it come here? Has it gone there? That's what I need to find out. Okay, that's the geometry. And for the geometry, if you notice that this point has come here. Now if I look at it, let's suppose that this member, this joint was not constrained by this member. Let's say that it's not constrained here. It's free to move. How would it move? If this joint moved here, to ensure that this member remains undeformed, okay, this would have to go up too, because then that would ensure that this was undeformed, right? Okay. So therefore, this point would move here if it was not restrained. Okay. But it is restrained. So therefore, obviously, this joint, since it's moved up this way, cannot move up this way. So therefore, what does it have to do? Now this joint has to move in this direction. But note that this member is this way. Now this point has come here. Now for this member not to actually deform, how will it have to go? It will have to go perpendicular to this member. Okay, perpendicular to this member. And that, where this and this connect, is where this joint actually is, to ensure that neither this member nor this member has actually deformed. Okay. So therefore, this is the point where this member is. Where is that point? Let's look at it. If you note that the way I have drawn it, with this as 5, this as 5, and this as 5, this is actually an 45 degree, 45 degree, 45 degree, and so this is a 90 degree. This is 45, 45. That's how I've managed the whole thing. So now, if this is delta, okay, when this has to move perpendicular to it, what does that mean? Perpendicular to this is this. So that means it moves parallel to this member. Okay. So this part is d delta. How much has it moved horizontally? Let's see how much it has moved horizontally. Okay. Now you have to understand that how much is this motion? Think about it. When you're going this way, how much is this motion? If you look at this, this is also 45, 45, so it's going to be, this is going to be d delta by root 2. Okay. Similarly, you will see that this is equal to d delta by root 2. And if you look at the horizontal motion, the total horizontal motion, it's going to be d delta root 2 by root 2. So that's going to be d delta by 2. Okay. So therefore, this point has moved vertically by d delta and horizontally by d delta by 2. Okay. So now I can write down my virtual work equations. So how do I write my virtual work equations? Let's look at it. The real forces undergoing the virtual displacements. Note that internal virtual work is 0 because the internal deformations, the virtual deformations are 0 because I've ensured that you do not have. So internal virtual work, even though under this you have real forces, the virtual deformations are 0. So the internal virtual work is 0. What is the external virtual work? First is this, RCY multiplied by d delta. Note that this is up, so the work done is positive. Now next, this force, F2, how much is it undergoing? D delta. But F2 is downwards, displacement is upwards, so it's negative work. Minus F2 into, actually this is the point, so this is the work done, and that is d delta by 2. So this is F2 into d delta by 2. Okay. And then the work done by F1. Okay. If you look at F1, the work done by F1 is negative because it's displacing in this direction, the force is in this direction. So minus F1 into d delta by 2. And that is equal to 0. So if you really look at it, you get that RCY is equal to F2 by 2 plus F1 by 2. This is what the principle of virtual displacement gives you. Let's see whether that is true by actually looking at equilibrium. Let's look at equilibrium, because there's a statically determinate structure. I can find out from equilibrium. Let me take moments about this point. See, note that this is our AY, this is our AX. Let me take moments about this point. So I'm going to take moments about A. If I take moments about A, what do I have? Let me look back at that particular problem. Let me go back. Note, this is 5, this is 5, and this is 5. F2, F1, and I need to find out our CY. So take moments about A is equal to 0. Okay. Take moments about A equal to 0. What do I get? R CY into 10. This is a counterclockwise moment. And both of these give rise to clockwise moment. So the clockwise moments are F1 into 5 minus F2 into 5 equal to 0. And R CY is equal to F1 plus F2 upon 2. Both the method of virtual displacement and equilibrium give me the same value of RCY. Okay. This, in a sense, is the method of virtual displacement. So therefore, what I have done is I have reviewed with you the method of virtual work, which actually is two different virtual work methods. One is the method of virtual force, which is used to find out displacements. Remember, let's review that. What did I use the virtual force method for? I used the virtual force method to get the displacement. Right? This is the virtual force. So virtual force method is used to find out displacements in the structure. And the method of virtual displacement is used to find out the forces in the structure using geometry. So that's the point that I was trying to make right at the beginning. The virtual force method is used to define geometry using equilibrium. And the virtual displacement method is used to define forces using geometry. We are going to continuously use these methods over and over again during the entire course that we have over here, and you will see how useful this method is. Note that some people tend to use the method of virtual work, some people use the method of stationary potential energy, minimum potential energy. All these methods, all of them are used to analyze a structure. Okay. They're used to analyze a structure, and these are just methods. All of them really give you the same. So you might have used the method of minimum potential energy to analyze the displacements of a structure. The Castigliano principle, okay, you've used that to get the displacements of structure. So what is so good about the method of virtual work? The reason why I am going to use the method of virtual work while I teach you structural analysis of statically determinate structures is because all the other methods are essentially mathematical principles where you need to differentiate something, you need to integrate something, and it's all mathematical. Whereas I like the method of virtual work essentially because it's very, very physical. You see, when I apply a force, I find out the forces. And then I use the virtual work principle, which says the total work done by displacements and forces in a structure under equilibrium is 0. The virtual work done is 0. So, in other words, when I use the method of virtual displacement, I actually displace the structure, physically displace the structure, find out all the displacements, and then all the virtual displacements I multiply by the corresponding real forces acting at those points, and I've got my work. See, it's a very physical way of getting what you have here. Similarly, the method of virtual force, to define geometry, you have so many different methods. The Castiglione principle, the conjugate beam, so many different ways. Why are we using the method of virtual force? Well, we're using the method of virtual force to essentially use equilibrium. All the other methods that you see are either geometry or mathematics. This one, you actually apply a virtual force, find out all the forces in the structure. Once you found out the forces in the structure, find all the virtual forces, you multiply by the real displacements and deformations and put that equal to 0, and you have unknown displacement that you need. It's a very physical way of obtaining the forces, and that is the reason why for the rest of the semester I'm going to be using the method of virtual work to solve all problems. And that is the reason why I have gone into this, spent one lecture looking at how to use the method of virtual work. Of course, today I just basically used it for a very, very simple problem. We will use the same methods to solve very, very complicated problems. Today was just illustration. So, this brings me to the end of the review section of this particular course. I have reviewed how to get the static indeterminacy. I have reviewed how to get the kinematic indeterminacy of a structure. So therefore, given a structure, you should now be very comfortable finding out the static indeterminacy and kinematic indeterminacy of a structure. I recommend that you go back, look at any book on structural analysis, pick up a few problems, look at them, and try to get the static and kinematic indeterminacy for those structures. Once you gain confidence, you will see that it's really trivial. Please remember, use the algorithmic way that I have discussed over the last 2 lectures of getting the static and kinematic indeterminacy. And today I reviewed the method of virtual work, which all of you are familiar with. All of you have used it. It's just one method that you have used to get displacements and forces in the structure. I am using it here because I'm going to be using it over and over again for the rest of the semester for getting your courses. I think I'm going to be ending here today because I would like to end the review module here. From next lecture onwards, we're going to be getting into the basic methods of analysis. And here I will, since I have a little bit of time today, I'm going to look at the methods that I'm going to be using. First, I'm going to be looking at the force method. Initially, I will be looking at the basic force method, which by now you should be familiar with, but I will still look at it because I'm going to be using the method of virtual work to solve the force method problems. So that will be the new way. Then I'm going to be introducing to you the matrix approach. You see, ultimately, the matrix approach has several advantages to the standard approach of force method. So I'm going to introduce you to the matrix approach of the force method. And I will be using the force method to solve truss problems, to solve beam problems, to solve frame problems. We are going to restrict most of the problems to planar problems because ultimately I am using them as illustration purposes. But all the things that I talk about are going to remain exactly valid even for space problems, space structures. So I'm going to look first at the basic force method, and then I'm going to be looking at the matrix approach of the force method. And in that, I'm going to be using the method of virtual forces, actually. The method of virtual forces to develop the equations in the force method. After that, I'm going to be looking at the displacement method for analyzing structures. Okay. In the displacement method, I am going to be using the method of virtual displacement to set up the equations that we are going to be solving in the displacement method. Okay. So this is the reason why I've spent today on the method of virtual work. It's going to be used over and over again. Again, in the displacement method, I'm going to look at the basic formulation, and then I'm going to be going into the matrix approach, which is essentially referred to as the stiffness method. The matrix approach for the displacement method is known as the stiffness method. So we're going to be looking first force method, basic force method, matrix analysis of force method, then we're going to be looking at basic displacement method, then we're going to be looking at the matrix approach for displacement method, which is the stiffness method, and that in essence will give you the overview of the basic methods which can be coded in the computer to solve complicated structural analysis problems. After that, of course, I'll be looking at a simpler approach which is known as moment distribution, which is how to solve complicated structures using hand calculations. We'll look at that. And finally, as I said, we'll be looking at influence lines, okay, how to obtain the loads, maximum loads, design loads in structures under moving loads. Okay. I end here today. Thank you very much. Meet up with you next time again. Bye.